Last time, we taught a model to remember the past, a windowed LSTM that watched a slice of history and predicted what came next. Today, we point that same instinct at people. The question changes from what happens next to what should you watch next. And we're back at two familiar stops on our pipeline. We build with embeddings and we predict by retrieval. This is how a streaming service narrows millions of titles down to the handful on your home screen. Remember when we turned words into vectors? Each word got a little arrow in space, and words with similar meanings ended up pointing the same direction. We're going to do the exact same trick, but now the things getting arrows are users and movies. Person becomes a vector, film becomes a vector. Same idea, brand new world. Here's the shape of the solution. Two separate little networks. We call them towers. One tower's only job is to learn a good vector for each user. The other tower's only job is to learn a good vector for each movie. They never share weights, but they aim at the same target. One shared vector space where users and movies can live side by side. And that shared space is the whole point. Once a person and a film are arrows in the same room, comparing them is trivial. Geometry does the work that a giant rules engine used to do. So, what does a good recommendation actually look like? In vectors, it's a user arrow and a movie arrow pointing the same way. We measure that with a dot product, high when they're aligned, low when they're not. A big dot product means you'll probably love this. A small one means keep scrolling. Now, how does the model learn those arrows? We never tell it what a good vector is, we just show it history, who watched what. For every real pairing, a user and a movie they actually watched, we nudge their two arrows closer together. Do that across many people, and similar tastes naturally cluster. People who love Pixar drift toward the same corner of space, and so do the Pixar films, because the same fans keep watching all of them. But pulling matches together isn't enough on its own. You'd collapse everything into one blob. You also need to push things apart. So for every movie a user watched, we contrast it against movies they didn't. The clever shortcut, every other movie in the same training batch, is a free negative example. Pull the real pair together, push the rest of the batch away. That contrast is what gives the space its shape. Here's the part that makes this scale to Netflix. At serving time, you don't run the model for every possible movie. You pre-compute every movie's vector once and store them. When a user shows up, you embed just that one user, then do a fast nearest neighbor search over the stored movie vectors. Millions of titles ranked in milliseconds because it's just geometry. Find the arrows closest to yours. That two-step move, embed everything offline, retrieve fast online, is exactly how Netflix and Spotify go from a catalog of millions to the short list you actually see. Build the space once, retrieve forever, let's go build it. One file, 3 short pages. Up top we fake a small movie length style dataset and map the string IDs to integers. Then we build the two towers with the functional API, train them on watch history, and finally embed every movie and rank the nearest ones to a single user. Watch the gold box walk each section. First, the data. We've got a tiny table of interactions, a user ID, a movie ID. Every row is this person watched this film. I've given 3 users overlapping Pixar habits on purpose, so the Pixar titles co-occur and end up neighbors. These are strings and Keras embeddings need integers, so we use 2 string lookup layers, one adapted to the user IDs, one to the movie IDs. Adapt scans the data and builds the vocabulary. After that, calling the layer turns Toy Story into an index the embedding can't look up. Now the user tower. It's a tiny functional model, a string input, the user string lookup, an embedding that gives each user a 32-dimensional vector, then a dense layer to refine it. That output, one 32 number vector, is the user. That's the whole tower. The movie tower is its mirror image. Same recipe, input, the movie lookup, its own embedding, its own dense. Separate weights entirely, but the output is also a 32 dimension vector. So users and movies land in the same sized space, two towers, one shared geometry. Here's where they meet. We wrap both towers in a small model, whose train step runs each side through its tower and scores them with a dot product. High score, good match. This is the scorer we're going to train. Training is the in-batch sample softmax trick. In train step, we embed the whole batch of users and the whole batch of movies, then take user vectors times movie vectors transposed. That gives a scores matrix, every user against every movie in the batch. The diagonal is the real pairs, so the right answer for row I is simply column I, and we use sparse categorical cross entropy with labels, range, batch size. Every off-diagonal entry is a free negative. One matrix multiply does pull together and push apart at once. We compile with Adam and fit for a few epochs. Loss drops as the model gets better at picking the truly watched movie out of the batch. That's our signal, the two spaces are lining up. Now we serve. We run every movie through the movie tower once and stack the vectors into one matrix. That's the index you'd cache in production. To recommend for user 42, we embed just that user, L2 normalize both sides, so the dot product becomes cosine similarity, score against all movie vectors, drop the films they've already seen, and take the top 3. The print shows the films and their cosine scores. And there it is, user 42, who loved Toy Story and Up, gets Finding Nemo, Ratatouille, and Wall-E, all high confidence, all Pixar adjacent, none of them hand-coded. Two towers, one shared space, nearest neighbor lookup. We've now spent this whole course predicting the next word, the next frame, the next movie. Next time we stop predicting and start acting. An agent that learns by trial and error, balancing a pole on a cart, rewarded only when it gets it right. Reinforcement learning is up next.